All right, we're going to implement a trie next, and it is pronounced try, not tree, for the sole reason of sounding different than tree when you say it out loud. That's deliberate. That is the reason. Um, yeah, so this isn't really an algorithm so much as just knowing what the data structure is, because it's not really covered in a lot of algorithms classes, mainly because it's not that interesting algorithmically. I don't think it's particularly novel, but it is used widely enough in the industry that they do like to test for it. I've never been tested for it, but it's in all the study materials, so I assume it is. I know a couple of guys who work in Fang. I don't personally, but they've all told me that they know what it is. They use it. They do expect you to know it, but uh, yeah. Anyway, so let's do it. So what a trie is a prefix tree. The idea being you can take some ordered sequence, usually a word, which is an ordered sequence of characters, and you can go in order through it and determine if it exists. And it's using like extra memory efficiency. Sorry, it's using extra memory to save time. So the idea being you could have a linear time lookup to see if you've already got some some prefix stored in a database. So for example, if you've got 1,000 letter long word, maybe you can go through just the first few characters in it and you'll know, okay, this doesn't exist, we don't have it, let's just exit out early. So it gains a lot of real world computation time back, even though it's not really in theory, the theoretical bounds aren't super great. It's still a linear time lookup in big O sense, but usually you're gonna exit out a lot sooner than that. The worst case scenario is more rare, even though it's still the worst case. So the version I like to do is with hash maps, mainly because that concept is a little more transferable between different languages. You might see some solutions where they'll do it where each each node in this graph, because it's a tree, each node in the tree has an array of maybe 26 characters, and that's pretty domain specific because that would only work for ASCII characters where you have a set number of them, 26, and you can just kind of assume, and that's it's fine. It's perfectly fine to do something like that. But I think a hash map is a little more general. It's got the same theoretical bounds, even though, okay, hash lookups still have a much higher constant time applied to them than an array, because arrays are very, very, very fast. But to do like a hash operation, some hashing functions are really nasty in terms of like how much work they are. Now, maybe the nastiness doesn't really come in if you're doing just like a couple of characters as your input to the hashing function. But yeah, some of them are really involved. Hashing is an extremely, extremely deep field, particularly when you start getting into the cryptographic ones where they're actually going to be um, where the worst case of like a linear time lookup in a hash. Those are much, much more rare in the kind of nastier hash functions that take more care to avoid collisions. So let's start actually writing something now that I'm done chewing your ear off. I'm going to import the right header file. So include. I can't wait until C++ editors and compilers start supporting modules by default without having to do weird compiler flags. But until then, we're going to go ahead and keep using this include keyword. So unordered map. And you specifically want unordered because that uses hashing as opposed to a regular map, which uses some kind of, I think, red-black tree, some kind of tree with logarithmic lookup time. Don't use that. Use unordered because it will give you constant lookup time. So our tree is going to have, we need our base thing. So it's going to be an unordered map. And we're going to have character keys. and we're going to have, actually, you know what, I think, here's what I'm going to do. I'm going to define the node type. So the node type is going to be the class or struct. I can never remember if I need to use like type def or like the extra, like when you make a struct, every time you use it, you might also need to write out struct again. I can never totally remember if that's the case. So I'm going to go ahead and do a class, and I'm going to make everything public, which basically makes it a struct. So public unordered map character, and it's going to take a pointer to itself. So try node pointer children. So the children of a trie node are you're gonna have this unordered map. You're gonna reference it by a character. So for well, yeah, we'll go through the example, but so if you've got the string ABC, let me write it out. ABC. Say this is your input word, and you want to know if ABC exists in the trie. Well, the first character you look up A, and then A is gonna have some children, and then you want B is gonna have some children, so it'll be a 3 depth level trie. A trie is a tree. It's a subtype of a tree. All right, so unordered map character. Let's call this trie node. Node root. The root of our trie. Children, not children. Typo there. Okay, nothing in the constructor because this is gonna be empty at first. It looks like we're adding 3 operations. Insert search starts with. These are pretty much the same. The difference between search and starts with is a kind of tricky bit that takes a little. It took me a little longer to grasp the concept of how to properly mark complete words. So how do you know when you're looking at a prefix versus a complete word? There's a couple ways to do it. My preferred method is to insert some marker into the children. So I usually I'll use a pound sign. If something has a pound sign as a child, that means it is a complete word. And you can use any character that is never gonna be like part of your words or whatever your strings are. That is an option. Another thing people sometimes do is give it like a Boolean field, something like that. I think it's a little less elegant because then every node has this field, as opposed to only the nodes that are the end of a word will have the extra memory used. It doesn't really make a difference in the theory. Use whatever method that you think is more intuitive and that you can kind of have a better handle on when it comes to crunch time. I like to use some character as the children. So let's do insert. This is probably the harder of the 3 functions. What are we going to do? We're going to start off at the root, and I'm going to make some pointer for it. So tree node pointer, let's call it P, I guess. Pointer equals, and it's the root. We're going to start off at our root. And then we're going to go for each character in word for character C in word. What are we going to do? We're going to see if the character is a child of this particular node. So the way that you do that is with find. So if p children dot find c not equal to p children end. I'm not super fond of this syntax that C++ does for lookups, because this particular syntax, it implies that it's going to be a linear lookup time. And I suppose with anything hashing, in worst case, it could be you're not really, that's really, really rare. Like the chance of having a linear lookup time in an unordered map where the keys are hashed, that's the same chance as like randomly breaking an encrypted message, just like randomly. It's extremely unlikely. It could happen. It can happen, but it basically never does. I think the order cryptographic hashes, you're usually looking at like a 1 in 2 to the 60th chance. That's a common threshold for a lot of security definitions. It's considered like the minimum. That's a pretty big number. I don't remember what that is in decimal, but it's unlikely. Um, but this is how you check that a key exists. I definitely like the Python syntax where it'd be like if c in p children, something like that. Whatever. Anyway, so if our key is not in there, if the child doesn't exist, we return false. Otherwise, we're going to descend into the next child. So p equals p children c. And remember, so p is a pointer. The values are also pointers, so this is valid. And then we keep on going, and if we never ever return false, let's add some brackets. If we never return false, then we're going to insert our ending character. So p children, just pick a pound sign. It doesn't matter as long as you're consistent, and it doesn't, and it's not possible for that character to be in any of your words. If p children, so that's gonna, and we're just gonna set it's a null pointer. We don't need to allocate the memory. Oh wait, this is insert. So okay, we're not looking to see. Sorry, I was getting ahead of myself. If it doesn't exist, we're gonna add it. We're not gonna return false. So if it doesn't exist, p children c. I was thinking of just going through like a search or a starts with function before. We need to actually create it. So speed child. So we're going to create the child. We need to allocate the memory. It's a pointer. So we're going to use new tree node, and that's a tree node with no children. So that's fine. I think. Do I use parentheses or not? I can't remember if it needs parentheses. I think it doesn't. I'll have to try it. Allocating the memory, and that's fine. It's kind of dynamic, which is annoying. Not annoying. It's bad practice to use dynamic memory if you can avoid it, but I don't really think it's avoidable in this case because we don't know how much memory it is until we passed in a word as our lookup. All right, so if the child doesn't exist, we create it. And whether it exists or whether we created it or it existed before, then we descend into that child. And then we add in the ending character. All right, so search and starts with are going to be very similar. Yeah, I'll go ahead and write it out instead of doing copy paste because I think that'll give you a little more time to think through the process that I'm going through when I'm coming up with this. So similar start tree, try node, p equals the root. And then we go for character c in word. We see if the character exists. P children, find c. If the word, so if it does exist, wait, if it, and this time we're going to see if it doesn't exist, we're going to immediately return false. And that way, when we get to the end of the function, if we haven't returned false, we can return true. P children. And So it's equal to this ending iterator. This returns an iterator. If it's equal to the ending iterator, that means the key was not found. So in this case, when the key is not found, we create the child. In this case, when the key is not found, we just exit. So if we don't exit, we keep descending. P child. And then this is a search. So this is the one where we want to find a whole word. So say say we're looking for the word A. Well, if we have a bunch of words that start with A, but we never called insert on just the word A, we're never going to have that ending character associated with A. So we do want to check for that. So so we're going to actually return p children dot find character pound sign, our ending terminating character, not equal to p children dot end. So we're checking if the pound sign character exists in the list of children, which would be the keys of the unordered map of children. And starts with is going to be very, very, very similar. In fact, yeah, I am going to copy paste for this one. I feel like there should be some opportunity for reuse, but it gets kind of tricky with these like Boolean return data types. If you just returned like a pointer, if it starts with returned a pointer instead of a Boolean, then I could do it. But they're so similar. So I'm gonna go ahead and I think the difference is return true. So it starts with does not care if we're looking for an entire, whole word, or if it's just, some input. It doesn't matter if it has a terminating character in the children. All right, so let me step through this mentally just to make sure. So we got a prefix. We start at the root, and we're going to descend through. So for characters in prefix, if we have the character as a child of the word, so of the p, if it's child of the current node, then we're going to return false if it doesn't exist, or we're going to descend if it does. And as long as we've never broken out early, so all of the children have existed, once we're done with the prefix, we return true. So that should be fine. It's kind of, I guess I can step through an example. Some of these, I don't know that I want to step through an example because this isn't really an algorithm so much as just understanding the data structure. You're never going to be asked a question like this in an interview. Honestly, since tries always have to be implemented manually, I feel like it's pretty rare to be asked to use them at all. Now, maybe you'd be asked some conceptual questions, but as far as coding questions, imagine having to implement all of this before you even do your algorithm. Like that would take kind of a lot of time. Like it would probably take you, between introductions and the little pleasantries, and depending on the interviewer, you honestly might want to just speed through those if you can, because if they're a newbie interviewer, they'll just like look at the clock and say they're not going to give you they're not going to say, okay, we actually started doing the coding question at 5 or 10 after the hour. They're just going to say, oh, we started the interview on the hour and it's now 20 minutes after. It took you 20 minutes. That's pretty common, and I think it's a shame. It's a crying shame that interviewers don't give you like the benefit of starting coding questions later. So that incentivizes you to just like be a robot and then get to the coding questions as soon as you can, so you can end as soon as you can. I hate that, but it happens. All right, so we'll step through insert and search, just kind of mentally using a little bit. So say we've got the word, I'll just do like a single word example. So say we've got, I'm gonna do apple, I guess. All right, so say we've got, all right, apple is the input. And then, okay, start at the root. The root has no key, so we don't care, but it's got some children. 4 character and word, so starting with A. If P children find, well, children of this root node is already empty. So this is going to be equal to, and oh, you know what? Find, this is wrong. This is why we're stepping through this. So find equals equal to n. So if it's equal, then the child doesn't exist. All right, so if the child does not exist, we're going to create a new tree node. And it's going to have no children. And we're going to keep doing that. So, and then we're going to descend. So starting from the root, and then we move on to A. A has no children, so we add one. P, P. So there's going to be 1, 2, 3, 4, 5 nodes deep. And then the 6th node deep will have that there as a, actually, no, it would be 5 nodes deep, and the last one would have this child here instead of having no children. And then search. We start at the root. We go through each character. We check if the character does not exist. And then, yeah, I don't think an example is particularly useful for this without like writing it out on a piece of paper and stuff, and doing kind of a long example, which I know y'all don't have the patience for. So let's just go ahead and run it. And it will, I should talk, oh, what did I do? Unordered, did I spell it wrong? Unordered map, yeah, I did spell it wrong. Which is line 6. All right, so insert linear runtime, potentially linear space. And theoretically, it is linear space. Uh, dot end. Linear space. Search is also linear time. Starts with his linear time. And this linear under the assumption that the hashing is constant time, which in the real world typically is, but I have had an interviewer before kind of harp on like, if you take an algorithms class, your professor will slap you in the face if you say that a hash table has a constant lookup time. Really worst case, it is linear. In the real world, is pretty much always constant. Did I fix all the typos? Give it a run. Okay. Yeah, so with this new keyword, you don't need to call the constructor. Anyway, let's go ahead and submit. Cool, cool. And then we'll mark it off. Thanks, guys. You have a beautiful evening.